So where we left off, I haven't gone over one thing, one important thing, and then one fun thing at the very end of chapter 29. And it's not as complicated. It's not as major. So this thing is the only thing that doesn't work for all types of waves. Everything else we've been discussing has worked for any type of wave. What are the two types of waves? Say again? Electromagnetic and sound waves. Okay, good. Those are examples of the two. Very good. An electromagnetic wave is described as a what? What type of wave? Transverse. Meaning the wave propagates perpendicular to the direction the medium vibrates. Remember, we started with a wiggle. Things can wiggle. A wiggle in time, it just goes back and forth. We get the period. How long that takes to complete one cycle is a period. The frequency is the rate, the inverse of the period. And once that wiggle propagates through space, now we have a wave. And it can do it like that, a transverse wave, which is an electromagnetic wave. And sound waves are what type of wave? Longitudinal, where the vibration is in the same direction as the direction it seems to propagate. It's along the same axis. So our sound waves go like this, and the wave travels towards you in the same direction of the compression and rarefaction. So everything's worked for those. The polarization only works for transverse waves because of that perpendicular transverse nature. Most people are familiar with polarizers. They've at least heard the term. Here's some polarized sunglasses. But, what they are in here, they're polarizers. It's essentially kind of like this. Because if you have a wave, what's an electromagnetic wave? It's transverse, but what's it made up of? What's it look like when we start, light? An electromagnetic wave is composed of what? Do you remember? I'll give you a clue. Electromagnetic wave. Electrons can be the source. Remember, the source of all waves is something has to be vibrating. For an electromagnetic wave, it's often the electrons. An electric and magnetic field. I showed you that animation where we had the electric field vibrating, and then we had the magnetic field vibrating, and they propagate together as a transverse wave. That's why they're called electromagnetic waves. Anyway, it's an oscillating electric and magnetic field. And they're transverse. So this is to help us visualize a wave. Think of these as, let's just pick the electric field. Let's say this one. The electric field is oscillating back and forth. It gets stronger, weaker, in the negative direction stronger, and then weaker, more positive, less positive, more negative, less. And that's the wiggle. And as it propagates through space, we get a wave, that electric field that we visualized before. Well, that can do it in any direction. You could have an electric field in this orientation, and it would go in this plane as it travels to you. Or this one, it can come. Each would have their associated perpendicular magnetic field, but they can be in any orientation. This is called an unpolarized wave because it can be in any direction. But if you send this light, this wave through a polarizer, which ones get through? All right. Only the vertical ones, like this. And so once the wave passes through the polarizer, it's now called polarized light. And you only get the electric field in one direction. That's what these lenses are doing. These look like this. Kind of like Venetian blinds or something, They just let the vertically polarized light get through. These are polarizers also. If you take a second one, Let's make them both vertical. You take your unpolarized light, it makes it through, and now it's polarized. Can it get through the second one? Sure. And we still see the light. What if we turn this one so that it's horizontal? So now it comes through, it gets polarized vertically, tries to get through this one, and it can't. So you wouldn't see any light over here. But do you see why it only works for transverse waves? So let's show you. Oh, that looks pretty. That's better. Okay. There's a nifty circle. Good enough. Normal light. Let's send it through, here's the axis. So this looks like this, vertical. You can see it gets a little dimmer, correct? Well, it should. We just blocked out all the other orientations. Let's send it through a second vertical one. This one's vertical also. It gets through. Now I'm going to rotate this one horizontally and put it in there. Right there. And it disappears. So vertical, horizontal. Whoop, too far. And disc appears right there. So now we know they're exactly perpendicular. That's what polarizers do. They come in handy. So they can block out some unwanted light, especially if it gets polarized. Here's something fun, just to throw you off. So light can't get through both of those right now. If I take a third polarizer and stick it in between, it reappears. And without getting too complicated, but it's a kind of a review for the final. If you have a polarizer like this, and light is trying to get through it that's vertical, it's a piece of cake. But if it's like this and you're sending vertical light through it, there's components of this vertical light onto this diagonal. Remember, we can draw perpendiculars, and there'd be smaller magnitudes of light that can get through. And now it's on the diagonal direction traveling. And then some of those components can get through the horizontal one. So when you, these are perfectly perpendicular, but when you put a third one in at a diagonal, you're allowing some of the components to make it through. Notice it'll get dimmer than with just the two, but now light can get through those two perpendicular ones because you've rotated it in the middle. So we can't forget about our components. We've dealt with a lot with velocities and things. So sunglasses, how do they work? I'm going to turn this one horizontally so it looks like this. So let's send horizontal light towards the screen. This is what's happening. Things that are reflective, especially non-metallic things. Let's see, let's do it here. You got unpolarized light. When it reflects off of here, the horizontally one gets reflected more. And the vertical one kind of gets absorbed. And so we say light, reflected light is partially polarized. And for most horizontal surfaces, it comes to our eyeballs horizontal. You with me? So it's trying to enter your eye like this. Like this. This is horizontal light coming at us. Ah, the glare! So what do? You take your sunglasses, and if they're horizontal, it gets through, right? So you make your lenses like that and block the light. Ah, see how it's dark? Light can't get through. If I turn it, see how it gets bright? Not blocking. Blocking. And so that's what polarized sunglasses do. They get rid of that glare because the glare has been partially polarized. That's polarizers. Any questions? Yeah?
Same idea as diffraction, right?
What do you mean by same idea as diffraction?
You bend it, where you add the medium in the middle, you're like bending the light.
Oh, when I inserted a third one in there? So if this one's vertical and this one's horizontal, it can't get through both. Put this in there. Yeah, you can think of it, it has the effect of rotating it, the orientation of that wave. So in that sense, yes.
You said it was horizontal, vertical. So how are they embedded in the material?
How's it do it? It's interesting. These are polymers, plastic, and they're in long chains. And actually, for this one that lets the vertical light through, the chains are actually in this direction. And it's the electrons. The electric field that comes in makes the electrons start vibrating because they resonate with them. And they absorb the electric fields in this direction. It's just like a red jacket. Resonates with what two colors? Something that's red, the red light's reflected off. That means what two colors are getting absorbed? Green and blue. They're resonating with something in that pigment, and it absorbs them. So these absorb the horizontal ones, the electric fields.
So it's not something you physically see?
No, this is just an analog to help us visualize. Yeah. But the gist is, all it does is let the vertically oriented electric fields pass through. But that's a good connection with resonance, though. I didn't think to mention that before, so thank you, Eddie. We'll do this as a break later. I brought these are diffraction gratings. And somebody asked about spectroscopy. Is that you? We'll show that. And then a hologram at the end of class. Tell me when 5 minutes is up. Make me stop so you can come down and look at this. This is the coolest hologram I've ever seen, personally, in real life. Holograms work by interference. It's basically all I wanted to show you, something cool, an example of interference. Long story short, they take a laser light and it goes directly to the screen or the film that they're going to record the image on. Then they split that light up first. One goes to the screen and the other bounces off or through the object. And then it comes onto the screen where the other light's at. Well, that's had a different path and it's gotten distorted by the object. So by the time the waves come together on the screen, they superimpose, and there's constructive and destructive interference, and they make those light and dark patterns on the screen, the film. If you then shine light back through the film, you can kind of get the reverse effect, the image back, like those smiley faces from diffraction. So they record an interference pattern on the film so that when you shine light back through it, you get the original object. But from any angle, because the light was recorded everywhere. That's the gist behind holograms. This is a cool one. So I encourage you to come see it at the end of class, because you can't see it from where you're at. So. All right, let's take some questions first. I have some clicker questions for review, and I also have the test in front of me to help me remember to say some things. But I want to turn it over to you first. Let's see anything bugging you. There we go. Lest I get caught up in this and forget to. No. You didn't come with any questions?
Yeah, in the homework, there is a question. I think they are related, but I am not sure.
Okay.
There's a question about the burned feet, the feet that they are red because they are sunburned, and when you submerge your feet in the water they change. They are not red anymore. But it's the other question, where the people can see from the airplane the surface of oil on the water, and they see a yellow color, but the scuba diving see what color? That's a question from the homework.
Wish I could find those to get it exact wording. Do you remember which numbers?
I think it's the number 19, 20, 21, one of those three. No, it's not 21. I haven't turned yet?
Peacock, waiting for. Yeah, I'm looking.
Did you answer that question?
Okay, here's one of them. It's number 20 on the last homework, the one that's due tonight. Because of wave interference, a film of oil on water is seen to be yellow to observers directly above in an airplane. So those above see yellow. What color does it appear to a scuba diver directly below? Okay, so that's a thin film, kind of like our soap bubble. But the idea is, okay, light's clearly reflecting back up as yellow. Yellow. So if yellow goes up, what colors are getting through? What two colors make up yellow? Red and green. So which one's passing through the oil and the water? Blue. So if you were underneath, you could see blue. So a lot of these, they can seem confusing, but it's all back to that color mixing. If you subtract some out, you'll end up with this color. So do review. I've been trying to encourage. You can figure out which colors combine to what, and if you take this one out, 'cause like the homework, there'll be questions like that on the exam. There's one I didn't bring up, but the book did. Let me just say, iridescence is another fun color. Iridescence is basically interference, like a peacock feather or the wings of butterflies. You get the color because of interference, which means some wavelengths are being destructively interfered and subtracted out of the light. So if you see a blue butterfly wing, that means the blue light's going in and coming back. What's not? Red and green. They're destructively interfering in the edges, the small scale spacing between the wings. It's kind of cool.
Yeah, because when you grab a hummingbird,
I don't do that often. Grab a humming. Yeah, I know. Yeah, the iridescence on their bodies is caused by interference.
yeah, but it's not, if you grab the hummingbird and you open the wings, you don't see the colors.
Oh yeah,
You know,
yeah. If you spread out the wing and get to yeah,
doesn't have a color. And only the
or if you get them wet,
wings have
you can
that.
get some wings wet or whatever. And if that fills in the spacing with water instead of air, we just change the speed at which light travels, because it slows down in water compared to air. It's delayed. And so that changes the wavelengths that get destructively interfered. Yeah, and the color can go away. It might not be in the visible range anymore. So yeah.
But it's interesting because if you grab a male or female, if you have it in your hand, you don't know which is male and which is female. And they are flying and you can see the color.
Let's see a red foot.
It's one of the first questions.
Okay.
The first book.
Anybody else remember this one? Help us narrow it down.
It's in the
There's
first
a
part.
sunburned feet. If you stick your sunburned feet underwater, what color they look like? Yeah.
Yeah, sorry, I was just spacing that one. Aha! Number 9. Look at sunburned red feet when they are underwater. What color will they appear? The options are more red, red, or less red.
Less red.
Why less red?
Because the water is going to, it's not letting the other colors.
Yeah, some of the way they're going to get absorbed by the water. What color does water usually look to us?
Depends.
When you have lots of it, like a lake or a pond or a swimming pool. Towards the blue side. That means the blue light is getting back out, which means red gets absorbed more by water. So if you got something red under the water, I would expect that red light not to get through it as easily. So they'll look less red. Does that make sense? Again, the subtraction thing. Other questions? You want some clicker questions in to review? Okay, let's do that. 20. Okay. Pick some that I thought would be appropriate to recover or re-emphasize. See what we do. Sound normally travels farther in air when the sound is. This has a lot to do with your water question while you guys are logging in. The red and the blue light underwater. They pass through the water differently. In that case, blue went further, gets through it, where the red is more absorbed. Similar things happen when different frequencies or wavelengths go through other materials. They go through them differently. They go at different speeds. That's why they refract at different angles and we get a rainbow. Also why some can interfere and some don't. But it's also how far they can get. You send red light through a whole lot of water, eventually none of it will get through. But it has to do with their frequencies and wavelengths. So now we're sending sound through air. Same type of thing. We're comparing the frequencies, the resonance or the energy, and how will that affect how it gets through? See what you guys think. 27 of you voted. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. See, you're all thinking A or B, and most of you think A. The A's have it. Hence the low tone of foghorns, the author throws in. Another way to think of this, the book explained it better than I did in the lecture, is those interactions again. High frequencies, there's lots of interactions. There's more energy there. They're vibrating faster, right? So that means the molecules are jiggling faster. They're going to interact with the air because that's what transmits it. And with each interaction, they lose a little energy because it gives in some momentum and energy to the air molecules. And so the higher the frequency, the more energy is transmitted to the medium. Thus, it won't make it as far. There's another way to think of it. Low frequencies go further. And yeah, that's why you have foghorns. Because they can be heard way out there. If you did a treble note, no ship would hear it. Or by the time they do, it's too late. All right, this one. A factory floor vibrates. And as a result, you vibrate because you're standing on it. What is this? The floor is vibrating, and it's making you vibrate. So this one had plenty of maybe new terms for you. See if we can keep them straight. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Resonance. The correct answer is not resonance. So good, we can differentiate. Resonance is when you try to drive something at the natural frequency it wants to vibrate at. So we have these terms, forced vibration, natural vibration, resonance. If you force something to vibrate, that's like the floor forcing you to vibrate. The floor is vibrating. You put anything on the floor, it's going to force that object to vibrate. If the object naturally wants to vibrate at that same frequency, it'll be at resonance. So I guess technically this could be resonance, but probably not. It's just annoying us. But remember my ruler? You could whack it and it would vibrate naturally at a certain frequency. So if I forced it to vibrate at that same frequency, it'll resonate. And when you're at resonance, that's where it takes the least amount of energy. The least amount of energy for me to put in to have a big effect. So the floor was just forcing me to vibrate. Didn't necessarily mean I was at resonance. Remember us wiggling the spring? We could wiggle it and force it to vibrate, but not until we hit those natural frequencies did we get the cool standing waves where we hit resonance. Okay. The phenomenon of beats is the result of what? What causes beats? Hopefully you remember what beats are. How's that? Wah, 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 wah. With the tuning forks, this was the demo I used for it. While I'm stalling, I'll review beats. You had two tuning forks. If they were slightly different frequencies, we heard beats. While we're at it, if the difference between their frequencies, let's say this one's 500 hertz and this one's 495 hertz, what will be the beat frequency? 500 and 495. 5, the difference. What if this one was 505? It's still 5. You don't know which side. Yeah, that's the beat frequency. That's the wah, 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 wah. You'll hear that at 5 hertz. Even though the individual tones are vibrating at 500 hertz, you'll hear it, the beat. So, okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 77 interference. Very good. It's those two waves interfering constructively and then destructively, constructively and then destructively, and that's the wah wah you hear because they're slightly different size waves, slightly different frequencies. Chapter 26, number 4. Which of these does not belong in the family of electromagnetic waves? So which one of those is not an electromagnetic wave? Hopefully none of you are going, wait a minute. I think 2 of those aren't electromagnetic waves. No, it's only 1. So you got a 50-50 chance. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. You guys all think it's sound. You're right. Sound is a longitudinal wave. It travels through the air. It needs the air. That's the sound you're hearing from my voice. The confusing for most people is radio waves. Radio waves is an electromagnetic wave. That's how the information gets to us from the radio station. It travels at the speed of light. Doesn't need the air to go through. That's why we can transmit with radio waves into space. Once it gets into your radio, it causes the electrons in the antenna to vibrate. That causes a current, which makes your speaker move in and out. What's your speaker do when it moves in and out? Pushes on the air. Now we have a sound wave that we can hear. You just, for now, write them on a paper or something. You can turn it in to me. Yeah, you just write them down. I'll give you credit if you do that. All longitudinal waves, you can think of compression waves, yes. There's something is being compressed and then spread back out in the same direction of the propagation of the wave. Sound is one example. Waves in a slinky that we did when we went this in and out, that's a longitudinal wave. There's some pressure waves from earthquakes that do that with the earth, through the earth. Cause the material in our earth to do that, and that's how that one's transmitted. They also have transverse waves, a second wave, which travel at different speeds, by the way, which is how they help figure out where the earthquake came from. All righty. Let's shine some visible light on a pane of transparent glass. What's going on when that happens? incoming wave hitting something that's transparent. Yeah.
On our cheat sheet, can we include like a color wheel
Yep.
like this?
Yeah. Yeah, you get that one cheat sheet. You can put on it what you want. So you might as well make it something that's helpful for you. I've seen some people write it down in the letters too, like I did on the board. Whatever. I thought about it, but I'm not going to wear my t-shirt during the exam. I think I wore it during the final one semester. That was fun. But
What are
anyway.
the restrictions on that? Is it just like one-sided, or does it matter?
I don't think I matter. Just one piece of paper. One, not bigger than 8.5 by 11. But yeah, if you want to use both sides, then sure. You still have to reason this stuff together. But it's a lot to memorize, I know. New terms. So we'll see if you can apply it correctly. That's what makes me happy. All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what we got. Ooh, most of you A. I'm proud of you. Good. I was worried about this one. So the light comes in, yeah, remember, and it absorbs it, bloop, and then it re-emits a different photon of light. It's not the exact same light that came in, but it's the same color, right? And then this one absorbs it, bloop, and re-emits. Yeah, so very good. So on those lines, strictly speaking, the light that shines on glass is what when it comes out the other side? Forgot this one was right after. I probably wouldn't have said as much. So hopefully that was your clue. How are we doing? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's the last person. 2/3 of you think it's B. Correct. Like I just said, it's not the same light that came in that comes out. Because they absorb it, and then their vibration emits. The wave looks identical, but it's technically a different wave. So we like to think of, I see the blue light from your jacket, and it just passes right through the glass of my lens. But it's really doing that bloop, bloop, bloop. And it's just the same frequency, so I still see the same blue light come through. So the slowing of light in transparent materials has to do with what? Hopefully we've just led up to this one too. So let's see, it doesn't give it away if I add, remember the speed of light doesn't change no matter what it goes through. But it obviously is delayed when it goes through things. Why? That's what this is asking. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you A, very good. That just takes time, and it delays it. And so the more it goes through, the more it's delayed. What? No, save that. I think there might be another question that I picked. That's right. Window chapter 27, number 4 I wanted. All right, to say that rose petals are red is to say that they do what? Something is red, what's that mean? Hope this is helping you. Okay. Test yourself. It's always good to test yourself before the test so you know what you need to study more. While you guys are filling this one out, friendly reminder, the book has those checkpoint questions, or check your understanding, I forgot what they call them. And the end of the chapter, all the odd questions have the answers in the back. So if you want to check yourself to see if you really got this, you learn a lot more in trying to recall than just, oh yes, I've highlighted my definition of diffraction. I know what that means. Maybe you can get a deeper understanding so when you have to apply it on the test. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. You betcha it reflects, which means it's absorbing the other ones. They resonate and get absorbed. All right? Test you on one of those color things. A mixture of magenta and yellow dots on a printed page will look what to us? So you got ink on the page, magenta and yellow mixed together. Just step it through. What colors make up magenta? What colors make up yellow? What's reflecting? What's getting absorbed? You guys aren't answering as fast, and I don't see quite as many searching through your notes. So I'll even tell you, magenta is red and blue light. Yellow is red and green light. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Red it is. Because red's the only one that reflects off of both, is in both. Or you can think of it as magenta is red and blue, so it's absorbing green. Green's gone. Yellow is red and green. It absorbs blue. Blue's gone. So the only one left is red to reflect back. Yeah.
This is actually one that was on the homework due tonight. I think it's around like number 12 or so.
Lay it on me.
The one about the red plate.
Number 11, looks like. When white light is shown on a red glass plate, the color that is transmitted is red. Does that make sense? Because the plate's red. That means red light's reflecting. But the color that is reflected off the front surface is not red. What is it? Your clue is that light. Why is the light, we see the glass is red? That means it has to interact with the red pigment first. That's in the plate. So light that goes into the plate and comes back out will look red. The light off the front surface has never gone inside. So it never got absorbed by anything. It's all reflected. So what color do you think it would be? White. Because it's reflected before it ever gets in and interacts with the dye. So yeah, there's your homework assignment. Go find some colored glass. Sure, it looks red. Look through it. It looks red because that's light coming through it. But look closely at maybe at an angle at the light that just reflects off the top surface. You can actually see two reflections, one from the front and one from the back. They'll be less intense because the one that went through it and bounced off the backside, some of it will get absorbed. And so it won't be as bright, but they'll be different colors. You should see white off the front surface because it never went in. Red that went through it. Does that make sense? Oh, you've all voted. Whoa. Oh, I haven't hit open, that's why. That's from last time. Duh. But you've had time to look at it. The color of light that passes most readily through a thick atmosphere is. That's our, why is the sky blue? Why are sunsets red connection? The particles in the sky are scattering. certain frequencies of light. It's proportional to the frequency. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we split. Red or blue? Okay, let's think it through. The light that comes from our sun, we'll use our sky, it's all scattered. What color gets scattered the most? Blue, because it has a shorter wavelength. That's why the sky looks blue. If you're scattering blue out of the white light, it's subtracted from white. What makes it through easier? The leftover colors, red and green, the longer wavelengths. So red passes through our atmosphere easier because it has that longer wavelength, the lower frequency. It's not scattered as readily as blue is. That's why our sky looks blue. It just scatters blue everywhere. But the red is getting through. That's why the sun looks yellow. And as it goes through more and more atmosphere, more blue gets scattered. It's maybe part of the green. And you're just left with oranges and reds getting through those longer waves. Okay, that's good because leave time. Let's pass these out. We got about 5 minutes. I'll tell you what, you can come up and do that. That'll be easier because you're coming up for the hologram. So what I want to explain these to you. Diffraction. Light comes through and diffracts. That means is this light, you're going to look at it back here, and you'll see the light spread out because of the different wavelengths. If this colored gas tube has different wavelengths in it, they'll diffract at different angles. And you can see that signature for different gases. And then we'll look at the hologram as well. But real quick, let me look at my exam here and see if I really wanted to tell you something. Oh, review refraction. What causes refraction? What makes something refract? It changes mediums. As it changes mediums, what happens to that wave? It bends. What's making it bend? Why? What's the root? Why does it bend? Right. It's that speed through it. And that's for sound or for light. And remember, we can refract it, whether it goes faster or slower. Remember we did an example with warm air and cold air? You also have water or oil. You could compare different things. But it can bend as it does that, depending on whether it goes faster or slower. Things go faster, and for sound, it's the interactions. So generally things that are more dense, because they're closer together, there's more interactions. For that reason, it needs the medium. So sound travels faster in solids than they do for gases. And for light, it's those interactions also that slow it down. So the more it has to go through, like water, there's more interactions. Or you heat something up, there's more interactions. It slows it down. It has the inverse effect. Did that. Review the relationship between wave speed, wavelength, and frequency. Could you calculate one of those if you knew the others? Wink, wink. Okay. Any last minute questions for you guys? Or you can ask me when you come down. Let's just let you come look. Helium's my favorite, so let's dim this a little. You bet. So this one, yeah, you can move around too.